welcome to our quantum deep dive.
Great to be diving in.
Today we're pulling back the curtain on a really cutting-edge technology, quantum optical coherence tomography, QOCT for short.
That's the one. And we're going to unpack it using a really insightful essay by Jörg Oschneppet as our main guide here.
Right. So think of this as, well, your shortcut to getting up to speed on QOCT.
Exactly. Our mission is basically to take the key ideas from that essay. What is QOCT? How does it actually work? Where might it be used? What's coming next? And just make it accessible.
And show why it's generating some buzz in science and industry.
Yeah, absolutely.
And the core idea, it really is a big leap, isn't it? Many people might know classical optical coherence tomography, OCT. It's pretty standard in medical imaging.
Standard tech.
But QOCT isn't just like OCT version 2.0. It digs into fundamental quantum mechanics.
Right. It uses entanglement, that weird quantum link in coherence, the wave nature of photons.
To get precision that, well, classical methods just can't really reach.
That's the promise. And the essay, Schneppet's essay, it really lays out the basics, gets into the technical side, the applications, challenges, the whole picture.
Highlighting why using these quantum effects is such a potential game changer for imaging.
Precisely.
Okay, so let's unpack that leap. Classical OCT that popped up in the 90s?
Around then. Became really important, especially in ophthalmology, for looking at layers in the eye, that kind of thing.
And it works by sending light in and seeing how it bounces back, right? Using the coherence of the light.
Pretty much. It measures the interference of light waves returning from different depths to build up a cross-section image. Standard wave interference.
But QOCT swaps out that, let's say, normal light for pairs of entangled photons.
Exactly. And that quantum switch gives you, well, potentially much better depth resolution. You can see finer details, deeper inside materials or tissues.
Okay, better detail, deeper, and better signal to noise, too.
And dramatically improve signal to noise ratios, yeah, which is crucial.
So less static, more actual image?
You got it. Less fuzz, more clarity, deeper down. The essay notes that people started playing with quantum effects for imaging back in the early 2000s.
Oh, that early.
Yeah, but the real momentum, the big progress, that's been driven more recently by better ways to actually create these entangled photon pairs reliably.
The sources got better.
The sources got much better. Which leads us right into let's call it the quantum foundation. Entanglement and coherence are the big players.
Entanglement. That's the spooky action at a distance thing, right? Two particles linked?
That's the one. Linked so that measuring one instantly tells you something about the other, no matter how far apart. They're described by a shared quantum state, not individually.
Okay. And quantum coherence. Is that different from just regular light coherence?
It's related, but specifically about the wave nature of quantum particles, their ability to exist in multiple states at once superposition, and for these probability waves to overlap and interfere.
Ah, so it's the quantum wave interference that's key.
Absolutely fundamental for QACT. This interference allows you to extract information with really high accuracy.
So it's not just light bouncing back, it's how the quantum states, the linked waves, interact.
Exactly right. Which brings us to quantum interference itself. It's the superposition of these photon wave functions leading to constructive or destructive patterns. Think ripples in a pond, but quantum.
Okay, quantum ripples. How does that help you, see inside something?
Well, the relevance is huge. By analyzing these patterns, QOCT can detect incredibly tiny differences in the optical path length, how far each photon in the entangled pair traveled.
Tiny differences.
Really tiny. And because you're measuring the correlation between the pair, thanks to entanglement, not just the brightness of the returning light like in classical OCT, the signal is much less bothered by noise.
Okay. The entanglement connection makes the signal cleaner.
That's a good way to put it. It allows for that high-res imaging data, even when looking deep inside materials that scatter light a lot.
Okay, that makes sense. So how do you actually build one of these things? What's the tech look like?
Well, the essay explains it starts, naturally, with making the entangled photon pairs. The workhorse method for this in QOCT is called spontaneous parametric down conversion, SPDC.
SPDC, okay, sounds technical.
The concept isn't too bad, though. You take a high-energy photon, usually from a laser.
A pump photon?
Yeah, the pump photon. You shoot it into a special nonlinear crystal. Beta barium borate BBO is a common one.
Okay, laser into crystal.
And inside that crystal, the pump photon can spontaneously split into two new photons with lower energy. But the key is, These two daughter photons are born entangled. Their properties, like energy or polarization, are linked from the start.
Entangled twins from one parent photon. Got it. What happens to the twins then?
Then they go into an interferometer. Think mirrors, beam splitters, common setups like Mach-Zehnder or Michelson interferometers are used.
Right, splitting and recombining beams.
Exactly. The pair gets split up. Usually one photon, the signal goes through the sample you want to image. The other, the reference, travels a separate path.
A reference path you can control.
Very precisely. You need to be able to adjust the length of that reference path with extreme accuracy.
Okay, so one photon probes the sample, the other takes a known path, and then they meet up again.
They're brought back together to interfere, but detecting this interference isn't like measuring normal light intensity. You need special detectors.
Because you're dealing with single photons.
Single photons, yeah. So you need really sensitive detectors, often avalanche photodiodes, APDs. They can register the arrival of just one photon.
Wow. Okay.
And the crucial part isn't just detecting photons arriving, it's looking for coincidences. You look for pairs of detection events, one from the signal path, one from the reference path that happen at almost exactly the same time, or rather, with the specific time correlation linked to their entanglement.
Ah, because they were born together, they should arrive with a certain timing relationship.
Precisely. You measure that correlation. The number of these coincidence counts tells you about the quantum interference and how the sample affected the signal photon.
Okay, so generate pairs, split them, one probes, one is reference, detect single photons, look for coincidences. How does that become an image, though?
Right, this is where the analysis comes in. You're not just measuring brightness. QOCT measures something called the second-order correlation function, usually written as G2.
G2, yeah.
This G2 function basically quantifies the correlation between the photons. It tells you about their spatial and temporal structure, and critically, how interacting with the object changed that entanglement and correlation.
So G2 holds the key information.
It's fundamental. Then, for image reconstruction, you use algorithms. These decode the information packed into that G2 function extracted from the interference patterns and coincidence measurements.
How do they decode it?
A common way is using an inverse Fourier transform on the correlation signal you measure as you scan the reference path length. Conceptually, this turns the interference information, which depends on path length differences, into a map of the object structure at different depths.
So analyzing how the sample messed with the quantum link lets you map its internal structure layer by layer.
You've got it. And naturally, putting together detailed 3D images requires very high-resolution measurement tools like spectrometers and quite a bit of computational power to process all that correlation data.
It sounds incredibly sophisticated. Powerful, definitely. But I imagine it's not without its difficulties. The essay mentions some challenges.
Oh, absolutely. Nothing this advanced is easy. One big technical hurdle is still the efficiency and stability of those entangled photon sources, making pairs reliably at a good rate without fluctuations. It's tough. Depends a lot on the quality of those nonlinear crystals.
And the detectors. Those single photon detectors sound specialized.
They are. Highly sensitive, yes, but also can be quite expensive. That's a practical bottleneck for making QOCT systems more widespread. Cost is a factor.
And what about noise? Quantum stuff is famously delicate, right?
Extremely. Environmental noise is a major issue. Things like thermal background heat, stray light, they can swamp the faint single photon signals.
CD shielding.
Definitely shielding, and often sophisticated algorithms to filter out noise from the data. Even tiny physical vibrations or temperature shifts in the lab can throw off the path lengths enough to mess up the interference measurements. It requires a very controlled environment.
Okay, challenges acknowledged. But let's shift to the potential payoff. Where could QOCT really shine? The applications sound almost sci-fi.
They do have that feel sometimes. In medical diagnostics, the potential is enormous, especially for things like early cancer detection and examining tissues.
Because of that high resolution and contrast.
Exactly. You could potentially spot very subtle structural changes inside tissue, maybe indicative of early-stage cancer, much sooner than current methods allow.
The essay specifically mentioned skin and breast cancer examples.
Yes, those are key areas. And also the ability to analyze nonlinear optical properties of tissues, which can differ between healthy and cancerous cells. And a huge plus, it's non-invasive.
Right, no cutting?
No cutting needed. You could get these high-resolution images of tissue layers without biopsies. The essay connects how that G2 function essentially gives you depth information, letting you build that layered picture.
Less invasive, potentially more precise diagnosis.
Yeah.
That's a clear benefit. What about outside medicine?
Material science is another major area. QOCT looks incredibly useful for analyzing nanostructures.
Seeing things on the nanoscale.
Right. Visualizing complex shapes, finding tiny defects inside nanomaterials with resolution below a micrometer. That's powerful for development and quality control.
And for understanding materials themselves.
Yeah. Characterizing optical materials, too. Studying properties like refractive index or dispersion by seeing how the material affects the photon spectrum and coherence.
Any other areas mentioned?
The essay touches on quantum communication as well, maybe using QOCT principles to characterize optical fibers, checking their coherence properties or losses, and of course it's a fantastic tool for fundamental basic research.
Just exploring quantum mechanics itself.
Exactly. Studying entanglement, coherence, how light and matter interact at this fundamental level, QOCT provides a new window into that.
Okay, looking forward then. The essay paints a pretty exciting picture for the future. What's next on the technology front?
Well, a big push is definitely on improving those entangled photon sources, making them brighter, more efficient, more stable. Research is exploring new materials the essay mentions, periodically polled lithium niobate, PPLN, as a promising candidate.
Better sources. What about linking QOCT with other quantum tech?
That's a really interesting direction. Imagine integrating QOCT with quantum computers.
For faster analysis.
Potentially, yeah. Using quantum computing power for real-time image processing. Or maybe connecting QOCT systems into future quantum communication networks for super secure, high-bandwidth transfer of that complex imaging data. Concepts like quantum nodes start to come into play.
More power, better connections. What about new science this could enable? New research avenues?
In biophysics, there's huge potential. QOCT might give us completely new insights into molecular processes inside living cells. Things like watching proteins fold, or seeing how cells interact with a level of detail we haven't had before.
And better ways to crunch the data.
Absolutely. Developing new quantum algorithms specifically designed for QOCT data could be revolutionary. The essay mentions the quantum Fourier transform as an example, which could drastically speed up certain types of analysis needed for image reconstruction.
Okay, let's wrap up with the bigger picture, the societal implications. The benefits for medicine for industry seem pretty clear.
Yeah, faster, more accurate diagnosis, better quality control.
Mm-hmm.
Those are major upsides. But, as the essay rightly points out, there are ethical and economic questions, too.
Like accessibility.
Exactly. These are likely to be very expensive systems, at least initially. Who gets access? Will it widen healthcare disparities? That's a real concern.
And with such high resolution,
Yeah.
any privacy worries.
The essay touches on that too. If you have non-invasive imaging that can see deep inside things with incredible detail, well, you have to consider the potential for misuse, like in surveillance. It raises privacy flags.
So it's about balancing innovation with responsibility.
Definitely. We need to think carefully about how this powerful technology is developed and deployed.
So to kind of summarize, QOCT is this incredibly powerful quantum technology. It leverages entanglement and coherence for imaging precision that goes way beyond classical methods.
Right. It builds on the foundations of OCT, but uses the weirdness of the quantum world to see finer details, deeper and with less noise. Huge potential in medicine, materials, basic science.
And our deep dive today was really shaped by that excellent essay from Yuri.
Yeah, a really solid overview for anyone wanting to get their head around this field.
It really is. And it does leave us with a thought, doesn't it?
Yeah.
Building on those societal points you raised.
Mm-hmm.
As this amazing quantum imaging tech gets better and better, giving us these incredibly sharp, deep views. How do we make sure everyone benefits? How do we ensure it's used for good and not just available to a few or potentially misused?
That's the critical question going forward. Balancing the power with equitable access and ethical use, definitely something to keep in mind.
Absolutely. Well, thank you for joining us on this deep dive. Goodbye.